Hi everyone, I hope you're staying safe from the coronavirus, but welcome to this machine learning video on logistic regression, which is a very popular method for making binary classification models. And I will explain to you what it is and how it works, and then I will also show you how you can implement this method on your own datasets using scikit-learn. I have my completed notebook here that I will use for reference, but I will also walk you guys through the coding in this live notebook. But before I begin, let me actually give you guys my plan. So I will divide this topic into 3 videos. In this first video, we will talk about the maths behind logistic regression. In the second video, we will acquire our data set and do some data visualizations. And then in the third video, we will actually do the remaining steps, so from 4 to 7. Let's begin with part 1. So logistic regression, what is it? Now, I'm sure we're all familiar with linear regression, and if you're not, don't worry, I will explain it in this video. But I have the Wikipedia page here, and it's basically a model that's very helpful when your data lies along a straight line, right? So it's very good at modeling that sort of behavior. So the way I like to think of it, logistic regression is the categorical version of that. So it basically combines your features the same way, so linearly, but it gives you a categorical output, right? So obviously the naming doesn't really help us because it's called a regression, but it's essentially a classifier, but just keep that in mind. And it is a form of supervised learning, so we need labeled data, so X and Y, to train this model. And the way it makes its predictions is by calculating the likelihood occurrence of events. So this is actually the most important concept that you guys need to understand. So to explain this, I actually made some slides. So this is the part where I explain linear regression, and it might be too simple for many of you, so you can skip forward if you want. But you can imagine that we have some data for age versus height, and we want to model this. So let's look at linear regression as our machine learning model, right? So if we ran linear regression on this, what it would do is plot a straight line, right? And every machine has some tuning parameters, and the way we tune this line is by using this mx plus b equation that we all know, right? And the tuning parameters there are the m and the b. And intuitively, the m, what it does is makes the line wiggle about its center, and what the b does is basically make the line go up and down, right? And this is in one dimension, so there's one x, but we can just as easily have multiple x's, and then we would require at least as many samples as dimensions to be able to model this. So there comes in our sampling problem with high dimensional problems. And this is basically this, right? So there's nothing confusing. So these x's just get multiplied with this beta matrix, which is basically the m, and this 1, if you notice, will get multiplied with the beta naught and give us the b term for all of them. And yeah, and then we actually have this extra error term sometimes to tune some noise, but don't worry about that. Just try to intuitively understand what the tuning parameters do, right? So let's move to a different problem where we still know people's age, but this time we would like to predict if they will purchase our new product or not, right? So a 0 would mean you did not purchase the product, and a 1 would mean that you were sold. So looking at the chart, we can clearly see there's some sort of a trend, right? So if you're older, you're buying it, but so let's imagine we're selling health insurance, right? So if you're older, you buy it. If you're younger, you don't. Makes sense. So if we were to model this, and let's imagine we have nothing in our toolkit other than linear regression. So if you were naive and you just ran a linear regression through this, you'd get that, right? So yeah, it just plotted a straight line through the most dense points, and at first glance, you might think like this is useless, right? Like, what am I to make of if you're 40 years old, you buy 0.7 times, like I don't get it, right? But there is a way to think of this line so it makes sense, and that is to think of it as a probability rather than an absolute value, right? So, okay, so all right, if you're 40 years old, that means you're not 0.7, you're 70% likely to purchase this product, right? And if you're 50, you're 85% likely. So, all right, that kind of makes sense. But we still have a problem with these endpoints over here and here, because we know probabilities cannot be greater than 1 or less than 0. So what is our model trying to tell us over here? So what it's basically saying is literally, if you're 60 years old, the model thinks you're 100 and something, 110% probable to buy this. So for us, that's the same as being 100, right? So we can fill this in with a straight line. We can fill this in with a straight line, and now we kind of have a working model, right? Just by running linear regression on this. So in the middle, we can calculate the likelihood. So this is the likelihood occurrence we were talking about earlier, and then at the ends we know it. So then we can set some threshold by saying, like, anything below 80, like if you're 70% likely, just tell me it's 0. I don't care. But if you're above 80, then tell me you're gonna buy it. And actually, as you'll see, the logistic regression model can actually report these probability numbers to you, so you can actually look at the probabilities for each sample and make your decision if you want to. But we usually set some threshold. If you remember, we had some tuning parameters, M and B, in our last model. But how do we tune this model, right? Because we made this up. We made this shape up by joining lines, and we can't really tune it, right? So the reason we could tune the mx plus b line is because we had an equation that was of a straight line. So for this, we just need an equation that has this shape, right? And luckily, there is an equation which has this shape, and that is the sigmoid function. So looking at it doesn't really give you a feel for it. So let's actually go to our live code and try to investigate this function. So I will import some packages. And then let's try to actually build this logistic function, right? So it takes one argument t, and then it returns that function. If I remember correctly, -1 times t, right? So let's just check back. 1 over 1 plus. Okay, so that's our logistic function. But now we need a bunch of x points to plug into that. So let's make that with NumPy. And let's take from -6 to 6 and put 500 points. And then the way I'll make my y is sort of a lambda function. So what this is saying is basically take every point in my x and run it through that logistic function I created up there, right? Plug the point in place of t. And then I want to store the answer as an array, so I can plot it versus the x. And now we can use matplotlib to actually plot it. And let's make that color red, all right? As you can see, the logistic function is very similarly shaped to this. Now that we have the formula, we can actually kind of change the t, right, to tune this. If this line actually ever annoys you, you can just put a semicolon there. But so this is the logistic function. So let's come back here. So one interesting fact about this function is that it was developed actually from ecology to describe population growth, because as you can imagine, as populations grow at a fast rate in the beginning, but then as resources and the population start balancing out, the growth slows down. So there's a very interesting paper here about the origins of logistic regression, so you can read that. let's recap. So logistic regression is a binary classifier, so it's going to return a 1 or a 0, and it's best used in binary cases. And it's a linear classifier. So if you don't understand yet what linear means, I have one last resource to share with you. So this is a Stack Exchange conversation that I read, and someone was kind enough to actually share a boundary they made with logistic regression. So as you can see, it's very apparent what I mean by linear, right? So it will always divide the sample space with the line, and you can see here the shortcomings that even though we had some red points here, the model didn't care, right? Because all it's able to do is draw a straight line. So we should keep that in mind when we use it. But some examples of where logistic regression works really well is in weather to predict rain, or you can use it for email, but people usually use naive Bayes for that, or you could even do image processing with it. So if you notice, I told you that the t was a tuning parameter, but we need to somehow incorporate our x and y in this, right? So what we do is, the trick is to actually take our mx plus b formula that we had earlier, which is just this, and then plug that in place of our t, right? So then we have this new function, which is basically the sigmoid function, but we have our mx plus b in there, right? And then we can have a multiple of these, and then basically we can make a classifier, but do the weights in a linear way, right? As with all models, this model comes with some assumptions, and they're fairly common. So the data should be free of missing values, and we will make sure it's like that by checking for them, and removing them if there are any. So the second one is, your response should be binary, so obviously, and then the predictor features are independent. So this is one common assumption a lot of models make, and it's not always true in reality, but it's kind of our job to choose features or engineer them so they're as independent as possible, right? And the last one is your sample size needs to be large enough. So so that was actually a very basic, almost intuitive overview of logistic regression. There's a lot more math regarding how you actually calculate the weights, and you can go to these extra math resources to read about them. This is Andrew Nick's class notes, and it's very extensive. He actually starts with linear regression here, and then he goes on to build on it, so it's very long and detailed. I have the CMU Carnegie Mellon notes here, and this is actually a great one. So and then Wikipedia, of course, right? And so with that, I will actually end this section, and in the next section we will actually start getting introduced to our data sets. So I'll see you there.